Hello, welcome back to Decaf-Math. I hope that you are doing very well today or tonight, whatever time it is where you are. Thank you so much for joining me here, and if you're returning, thank you so much for your support. Welcome back to my math nook. So, let's jump right into some math together, shall we? So today, let's go over integration by substitution, also known as U-Substitution. So this is another method that we can add into our toolbox to help us evaluate integrals. So we've already done integration by parts, or at least we mentioned them. We haven't really practiced together, but we've talked about integration by parts. If you were able to follow along with that video, then U-Substitution today probably won't be too hard for you, I imagine. Usually when this stuff is introduced for the first time, it's taught in backwards order, or rather, we did it in backwards order. So usually you'll start with basic integrals, then move on to U-Substitution, and then integration by parts. But on that day, I was inspired by integration by parts, and today I'm inspired by U-Substitution. So we'll just do whatever we want around here. But maybe that video will help clarify things in this video, and this video might help with that video, so feel free to jump around as you need. And of course, if you need to review and practice some basic integrals, you can also check out my colorful basic integral video as well. So, U-Substitution. Okay, so let's start. U-Substitution. Okay, substitution. So for integration by parts, we had 4 things we needed to find: U, dv, v, and du. This is actually just u and du. Okay, so let's start with an example and build a little bit of intuition about why we're doing this. So let's do something like the integral of e to the 3x plus 2 dx. Okay, so this integral with respect to x. So if you know your basic integrals, and let's say we don't know about U-Substitution yet, if I were to say find this integral, you might look at this and go, oh, I know. This is actually, well, the integral of e to the x is e to the x plus c. It just happens to stay the same. So you might go, and I'll just leave a little question mark here. You might go, oh, well, e to the x, the integral, that's e to the x. So e to the 3x plus 2 is probably e to the 3x plus 2 plus c. And I'm putting a question mark there because I'm like, that's probably not right. But this would be a very valid guess up to this point, assuming that we only know our basic integrals. Well, the integral of e to the x dx is e to the x, so e to the 3x plus 2, the integral of that must be e to the 3x plus 2. Now, remember, the integral is really the which means whatever we get, the derivative of this should be the thing that we're trying to find the integral of. So let's say this was a very valid guess. It makes a lot of sense. But let's check if this is really the correct answer. Let's take the derivative of this. So how do we find the derivative of this? When we go, oh, e to the something, I know the derivative of that, so we're going to go backwards to check our answer here. So d of dx, which is the derivative, of e to the 3x plus 2. So we get e to the 3x plus 2, because the derivative of e to the something is that. That's it? Think. Are we missing the chain rule? We're missing the chain rule. Why is that? Because the chain rule helps us to find the derivative when we have a composition of functions. This is e to the something, but that something itself is also a function, so it's e to the 3x plus 2. So we have to apply the chain rule if we're going to take the derivative of this thing. So we also need to multiply this by the derivative of 3x plus 2, which is 3. Exactly. So we can pull that 3 to the front if we want, but this is our derivative. Now, is the derivative of this, is this thing equal 3e to the 3x plus 2 equal to what we're finding the integral of? Not quite, right? We're missing a factor of 3 here. So not quite, or a multiple of 3 here, right? There's no 3 in this one. So that gives you some intuition about why just finding the basic integral doesn't work. But this also kind of shows you that this U-substitution technique that we're about to use and find is kind of the equivalent of the integral version of the chain rule. So the chain rule is used to find derivatives of compositions of functions, but it's for derivatives. The backwards version of this is U-substitution. So let's go into how to actually use U-substitution to find this integral. Okay, so let's see here. The key thing is, for integration by parts, we had 4 things we needed to find or calculate. U, dv, ev, and du. Here, we only need 2. We only need u and du, okay? And of course, you can get one from the other. But specifically, because we're doing U-substitution, we are going to let u be something in terms of x. Our goal is to convert our original integral problem that's in terms of x, okay, some function of x dx, completely in terms of an equivalent integral, but that's all in terms of u, hence U-substitution. If we pick convenient u's, okay, or a convenient u, this will make our integral much easier to solve. That is our goal. So we could substitute whatever we wanted for u, but that might not simplify the problem. Much like for integration by parts, we want to pick and notice patterns that make our lives easier. So our goal will be then to make this now an integral completely only in terms of u. Then we can substitute back to get our answer in terms of x. So here, this is a natural piece. So we can say, okay, our problem here is the fact that we have e to the stuff, right? It's not just e to the x or e to the u. I just have a bunch of stuff here. Well, I might as well just set that bunch of stuff to equal u. So we choose let u equal 3x plus 2. Again, if we wanted to, we could let u equal 10,000 x cubed minus pi x whatever we want, but that's not going to get us anywhere here. But if we let u nice and simply equal 3x plus 2, this thing now becomes e to the u right here. But we also need to deal with this dx, okay? Because we can't just leave it like this. That doesn't tell us anything. We have to have this in terms of du. So from this u equal 3x plus 2, we can calculate du, just like we did with going from dv to v and u du for integration by parts. But here, if u equals 3x plus 2, du equals the derivative of 3x plus 2 is 3 dx. Okay? And the idea here is you can kind of think of it as if you have u as a function of x, you can do du dx is 3, and then move the du or the dx over. It's not technically correct because by the time we get to this d, we're talking about the derivative, not delta. So there's a very slight difference between dx and delta x, the change in x, but it's okay. The idea is still the same. We're essentially taking the derivative on both sides. Just make sure that you remember our goal is to get dx in terms of du. Okay, so u equals 3x plus 2. From that, we can get du equals 3 dx. So essentially, you take the derivative with respect to the variable on the side that you're taking the derivative on, and then throw in a du and throw in a dx. Okay, so from here, we now know that dx equals du over 3, which we can plug into this dx. So this dx is du over 3. Now we've completely turned our original question into a question in terms of u. Now we can notice, okay, well there's 1/3 here, so I'm going to pull that out. That is an integral property. We can pull out a constant. There are a lot of rules that you cannot do. Not rules, but there are a lot of things that you cannot do. For instance, just multiplying integrals, like distributing integrals, but pulling out a constant is something that you can do without breaking anything. So I'm just going to go ahead and pull out that 1/3 integral e to the u du. Okay, so again, we have our two pieces. We let u equal something. From that, we calculate what du equals. We should always have a du on this side, a dx on this side, and if we need to, we can rearrange the du dx to simplify this question, but we don't always need to. So we have our two parts. So now that we've substituted, we have a problem in terms of u. This we do know. Now we have our basic integral. What's the integral of e to the u du? It's e to the u. And then we put in our plus c for constant. Now, is this our answer? Well, not totally, because the question had an x. Our question was everything in terms of x. So if we answer in terms of u, it's kind of like, well, what's u? That doesn't mean anything. We're using U-substitution to help us, but that doesn't mean anything in terms of actually finding an integral. So all we do is we plug our u back in, which was 3x plus 2. So our final answer will be 1/3 e to the 3x plus 2 plus c. So this will be our actual final answer. Okay? So now if we take the derivative of this thing, basically we would have e to the 3x plus 2. The derivative of that would be e to the 3x plus 2. And then we have a times 3, but that times 3 cancels with this 1/3 to give 1. So then we would just get our e to the 3x plus 2. So we took care of the coefficient that comes along from doing the chain rule. Isn't that cool? And then our c is our constant for when we do indefinite integrals. Okay, so we pick u to simplify things, but really we also need to keep in the back of our minds that we also want to have du in this. So let me give you another example where there are multiple ways. Like this one seems a little bit straightforward into what to pick for you, because what else is there to pick? Like there's no other thing here, and so it just kind of seems like that would be the only thing that makes sense, because it doesn't make sense to set the whole thing equal u, because that's just the original question. So you might as well pick this. But let's find one. Let's do an example where it might not be quite so straightforward, but gives us a sense of what we're picking for u and du. Okay? Okay, so let us try. Let's see if I can come up with something. The integral of cosine of ln x over x dx. Okay? Like this. So now it's like, well, what do we even pick for u? Like, do we use u equals 1 over x maybe? So here's the thing. Remember that our goal is to write everything in terms of u and du. So this is where we have to give it a little bit of thought. If, and kind of just like plan ahead a little bit. So if we pick u equals 1 over x, okay, 1 over x here. If we think about what is du, then it's going to be, well, 1 over x is x to the negative 1, so you can use your x to the n rule, so negative 1, so negative x to the negative 2, so negative 1 over x squared. That has nothing to do with anything else in the problem, so that might not be a good use of u. But if I pick u equals something in here, I want to have like a piece of this be du and a piece of it be u. So if we let, for example, u equal ln x, and so this is just the way that I think of it, and I think it makes things a little bit easier. And it might kind of give you a little bit of a direction, because I know that when it's just really open-ended, it can be kind of confusing of what to pick. But I like to think of it as whatever I choose, like u equals my ln x, du would then be, and this is knowing what's the derivative of ln x, it is 1 over x. Okay, so 1 over x, and then we put in our dx. So the reason I wrote it like this is because 1 over x dx is du. But do we have 1 over x dx? We do. It's this thing. 1 over x dx is this. So when we do our actual U-substitution now, we have the integral, we still have our cosine of ln x is u, so cosine u, and then our du is 1 over x dx, so this whole stuff is just du. So this whole thing just simplifies to cosine u du, which we know what is the integral of cosine u du, or cosine x dx, whatever. It is sine. It's just positive sign, right? Sine u plus c. Okay, so this goes down to our basic integrals, but we can't answer in terms of u because our question was in terms of x. So we plug our u, which was ln x, back in. So our final answer would be sine of ln x plus c. That is it. That's it. So how do we check this? Well, the derivative of sine of ln x would be this is the chain rule. So sine of ln x would be cosine of ln x, but then we have to take the derivative of this thing, so cosine ln x over x, which is that. So we're good to go. So by keeping track of u and du simultaneously, we break up this part to be du, and then this part is our function of u, whatever that is, some function of u. We can take the normal integral. So it really is the backwards of the chain rule. Okay, so I hope that kind of makes sense. So I think this will probably get you on your way to doing some problems in practice with U-Substitution. The goal will really just to be practicing keeping in mind what your U is and what du is. You're going to have to think ahead and see if you can break apart parts of your problem to include that. Or if you don't specifically have du per se, but let's say you had some kind of constant. So let's say there was, like, I'll do this in a different color, not confuse us later, but let's say there was a 2 here. Remember, we can just do, this would be du over 2, for example, right? So even if you had a constant, that doesn't bother us because we could pull out the half, okay? So as long as we have like some constant multiple of our du, that's okay too. But that's our goal, because you don't want our goal is eventually to get rid of all of the u's, all of the x's, so you don't want to have a u substitution that's only halfway there. You don't want to have like some x's and some u's, like cosine u times x squared du dx. That's just not now. Get rid of those x's. Oh my gosh, I'm such a dork. Okay, but yeah, just get them all out so that you only have u's. Okay, so so you have the u, and then you can find the integral based on u, and then you can plug back in what you let u equal in terms of x, and then you can plug the x back here, okay? Okay, so I hope that this is helpful. I wanted to also bring up 2 little points that come up quite often, I think. One thing is that we've been doing indefinite integrals, meaning we haven't worked with bounds here and here, or here and here. So, but if we had numbers here and here for definite integrals, for example, if this is like e and to e squared or something like that, then when we convert everything in terms of u from x to u, we also need to plug in the bounds for u. Okay, so it's like changing the variables. This is kind of like an example of changing variables, but we also need to check the boundary points, right? We can't just say, oh, this is from e to e2 e squared, and then this is from e to e squared. That doesn't make sense because we've changed the entire question in terms of u now, which is our goal. Okay, so just a little thing, reminder there, if we do have boundaries, to be careful of what they are. And the second point is, I've also heard of people thinking that, you know, the example before where we had the 1/3 with a negative 1/3 in the front or what was it? I don't think there was a negative, but I think it's like 1/3 e to the 3x plus 2, right? So they will say, oh, well, they make the association with 1/3 and 3. So they'll say, okay, like those are related. So if we have an ln x, it must be 1 over ln x. But remember that that's actually just coincidental, because in that case we had a constant. It was a linear thing, so 3x plus 2 is linear, and our derivative would just be a constant number. But we have to focus on the fact that the derivative of ln x is 1 over x. So it's just coincidental that it's 1 over 3 in that case, and it's not that case for here. So, and also, if you, for whatever reason, decided to add another factor of 1 over ln x, when you, or like another multiple of that, when you take the derivative, you're actually having to use the product rule. So that's different. If you have a constant and you're taking the derivative with a constant times something, you can pull that constant out. But if you have another function, then you have to use the product rule, so you can't just take the derivative of each part. So fundamentally, it was only a coincidence that it was a 1 over. Just wanted to clarify that in case that brought up any issues. The key is really just finding your u, find your du. Hopefully you have some kind of product of those two. If you don't and it doesn't simplify, you could try picking different u's, and not all integrals are u-substitution problems. So but that's the general intuition that you'll use if it is a u-substitution question. Okay, so let's erase the board. Let's clean it nice. Okay, so I hope that was helpful and gets you on your way to doing some practice problems. Let me know if you have any questions, and of course as always, I hope I didn't mess anything up, but if I did, don't hesitate to let me know. And nicely, please. But I hope just in general that this clarified anything that you might have been still kind of confused with, or just anything really, or this might have been good review for you. But thanks for hanging out with me, and as always, let me know if there are any styles or practice problems or anything that you would like. I collect topics. I don't want it to become a chore, so I've been kind of taking my time for when I feel particularly inspired or think a certain style would be relaxing for me, and then let that convey out for you and hopefully here in this channel. But I hope over time this is a space that you will come back to over and over again for relaxing math. But if you do have any specific math that you kind of want to learn or relearn or review, it doesn't matter what level. Well, it does matter, because if it's too hard, I'm not going to know it or remember it. But this is a nice little community that we're building here, and I know there are at least a few grad students here, so I'm counting on you all to help me out here. But I will see you around, and I hope that you had a nice time, whether or not you're actually learning this stuff. It's great to have you. I'll see you. Bye bye.